there, my name is Che-Ting. You can call me Dakota, and today we're going to be creating a personalized chatbot in the Colab Pro environment together. This chatbot is fine-tuned with QLoRA to enable efficient fine-tuning, and it'll be deployed with a simple RAG capability. To start, we can look at the table of contents. There's two main parts, fine-tuning and deploying RAG. For fine-tuning, you load a pre-trained model, find a data set of your choice, and then you go into training. Then we'll see what it generates. Then we will implement the RAG with cosine-similarity retrieval. Then we'll compare the RAG generation with previous generations. Okay, so let's dive right into it. To start with, we have to pip install all these necessary packages. I'm using the Hugging Face frameworks and bits and bytes. Okay, so starting by loading the pre-trained model, here I'm choosing a GPT 20 billion sized model. This is about as large you can train on a Colab Pro environment. You have to use bits and bytes configuration here to load it in half precision, so it goes to around 40 gigabytes so that it'll fit in the Colab environment. So once you configure the bits and bytes, chosen your model, here you can load the model and its tokenizer in from Hugging Face, Okay, once we're done with loading the models, we will be importing this prepared model for K-bit training from PEFT. What this model does is a pre-processing function to enable your model to be trained in half precision. Once we're done with that, we will be defining a customized print trainable parameters function. This just shows you how much percent of trainable parameters there are in your model. Okay, so then we will be using it here. So here we will configure the LoRa. So what LoRa is, it's a efficient fine-tuning framework where instead of training the last few layers or adding a few fully connected layers to your neural network, you will be adding some much smaller adapter blocks to your LLMs. So these blocks will tell you, okay, which weights they should focus on for this specific task. So for here, the R is the attention max. Here we choose 8, and these LoRa alphas are the alpha parameters for LoRa scaling. Okay, so we choose it to be 32, and then since we're training here, so we set the inference mode to false. Then we will get our model. Then we print the trainable parameters, and you can see that trainable parameters here, the ones that we're going to actually fine-tune, is only 0.08% of the entire model, which makes it a lot more scalable. Then we're going to be loading in the dataset. Here I'm choosing the ArcSight CSML dataset from Hugging Face. It has about 50,000 questions and answers. The reason I'm choosing this is I want to test this on one of my graduate course paper critiques. I want to use this as an assistant, so you're free to use other datasets if you want to. I really recommend using the Hugging Face dataset. Even if you want a customized one, you can prepare it and upload it to Hugging Face so that other people can use it. And the load dataset function is just really convenient. Like here, it creates the train test split automatically. Here I'm defining a pre-processing function where I will truncate the input and output to a maximum of 512 lengths, and they will be tokenized with the model tokenizer. Once the data set is done, we will be going into the training step. Finally, we'll be going into the training step. Here, I'm using the transformers.trainer function to train my model. This is really a simple way to train your transformers, which saves you a lot of the repeated code in PyTorch and TensorFlow. So here we're using warm-up steps as 2, so it'll have two iterations to warm up, and then it'll stop at 50 iterations. I set the learning rate at 2e minus 4. Feel free to use other parameters or try other parameters if you want to. Okay, so here we start training. The training takes about 15 to 20 minutes and uses up all the GPU RAMs a Colab Pro environment can provide. Once you're done with the model, you can use model.save for trained to save this model and publish it to Hugging Face so other people can see your model and try them out. Now that we have our model, we can see how it generates. So here we're setting the configuration to inference mode, and then we will just be asking our model a query. What does retrieval augmented generation RAG do? And then we will be using a GPU device. So we have the model.generate, and then we will be setting the maximized output sequence at 50 because I don't want it to run for too long. And then we decode it. We'll see that the answer is related to the question, but it's a little vague. Okay, so we'll see what RAG can do for us. Okay, so first to implement RAG, we have to retrieve information from sources outside of the LLM. So I will be uploading PDFs to the drive, to my Google Drive here. And then here I'm using PyPDF, the simple read PDF function, to read in all the contents from the provided PDF, rag.pdf, which is a paper, the original paper of RAG. Okay, so then I define a class RAG retriever. So I will be building a simple RAG retriever on my own. I'm using cosine-similarity here. So it'll be using BERT to embed the sentences from the RAG paper, and then embedding the query to, and then computing their cosine similarities. I'm using batch encode here, and then the batch size is 128, so it's a lot faster than doing this sequentially. So for the retrieve part, we just really arc sort the cosine similarities and take top k relevant sentences to the query of your choice. Okay, so we can see here the RAG retriever is built, and then it batch encodes the whole PDF, and then we'll see what top 10 relevant sentences are there. Oh, so we can see we conduct an empirical RAG experiment across hundreds of questions. Before RAG, we can convert large documents. These are really relevant information explaining what RAG is and some of its performances. Nearly 47% of the question, 38% of the cases. Okay, so next we have to modify the generator a little bit. So we define another class of RAG generator. So you will be taking those RAG retrieved sentences, these 10 sentences right here, and then put them into your query template. So here it tells my LLM that you're given some metadata on this question, and then you will be using them to answer my question. So the LLM will less likely to be hallucinating, and it will be extracting information from the top K information sources that you provide. Okay, so here we can see the LLM's answer. It becomes a lot more coherent and explaining what RAG is. RAG is a method of converting large documents into retrievable content. The conversion involves several steps. And then I think it's trying to show a figure here, but sadly I'm not implementing any image capabilities here, which can be done later. Okay, so here we can see the answer of the LLM is a lot more contingent to explaining what RAG is. So it's a method of converting large documents into retrievable contents, which you can see it's extracted from the retrieved outside information. So that's how RAG reduces hallucination. Of course, this is still not that coherent. It's nowhere near the SOTA models right now. This is only 20 billion parameters and just fine-tuned on 50,000 data points, which is nowhere near like all the data that they like they trained the 135 billion GPT 3.5 on. But this is a good way to practice how to fine-tune your model and implementing RAG, the concept of RAG in an affordable environment. Thank you.